In this video, we'll be introducing probability. So to start off with, I'd like you to meet Alan and Bob. So Alan and Bob are playing a game. Each of them pays $30 to start the game. Therefore, there's a total of $60 in the jackpot. Alan and Bob have an equal chance to win. That is, the probability of Alan winning is 0.5 and the probability of Bob winning is 0.5. Whoever wins 3 games in total wins the jackpot. Alan wins 2 games and Bob wins 1 game of the first 3. However, something happens and the game is interrupted. As they are unable to continue playing, they need to divide up the jackpot based on the current results. So our question is, how do you think the money should be divided, given that Alan has won 2 games and Bob has only won 1? So take a minute now to think how you might split it up. So a possible solution to this. We could split the money in a 2-to-1 ratio. The logic behind this being that Alan would receive $40 as he won 2 games, and Bob receives the remaining $20 as he won only 1 game. Maybe you thought of this, maybe you didn't, but do you think this seems fair? So this solution is a very intuitive one, where it's based on simply ratioing out the money so that it goes equally to the number of games that each person won. But what we need to do is we need to think mathematically about what's going on. So to do this, let's consider the probability of Alan and Bob winning from this position. So Alan's already got 2 games and only needs 1 more win to secure the money, while Bob's only won 1 game and would need 2 more wins to secure it. So therefore, there's a maximum of 2 more games that can be played. So we're going to use a tree diagram to set this up. So the tree diagram is going to say that if the first game is played, Alan could win or Bob could win. Now, if Alan wins the first, it doesn't really matter if they play the next one because he's already won. But even if they decide to play the next one, Alan could win again or Bob could win. If Bob won the first game, Alan could win, meaning that he wins overall because he's secured 3 games to Bob's 2, or Bob could win. And finally, Bob would have 3 games, the only outcome that leads to that, meaning that he would take all of the money. So, if we have a look at what this means, our sample space can be written as, and we're going to use these funny curly brackets, which indicate set notation, which we'll see a little bit more of in a minute. But we could have AA, AB, BA, and BB. And this just comes straight from our tree diagram. So as you can see, 3 outcomes, 1, 2, and 3, all lead to Alan winning, because in each of those cases he gets to 3 games first and Bob doesn't. And then there's only 1 outcome that would lead to Bob winning, which would be the final one. If we look at it, we can see that Alan has a 3 out of 4 chance, or you could think of that as a 75% chance of winning, whereas Bob only has a 25% chance of winning. So therefore, how would you split the money? So from our mathematical solution, the fairest thing to do would be to split it in a ratio of 3 to 1. So based on our mathematical solution, the best thing to do would be to divide it in a 3 to 1 ratio, where we would say that Alan would get 3 parts out of 4, so that would leave him with $45, and we would give Bob then the remaining $15 or a quarter of it based off the probability of them winning from the situation they found themselves in. So what did we learn from that? We saw that Alan and Bob introduced us to the concept of a sample space, and that's what we were setting out with a tree diagram. So the sample space of an experiment refers to the set of all possible outcomes, and we denote that with this symbol here. So that symbol's been simplified. It should technically be something like this, but that's sometimes a little bit hard to write. But we just simplify this to be a curly sort of E shape. So events, we call an event something that occurs within the sample space, and we label that with a capital letter as a general rule. So capital A, B, C, and D can be used. Set notation can be used to represent the events in a sample space. And we've already seen some of the notation behind set notation. And that is, we use these curly brackets here and a curly bracket at the end to list off all the events in our sample space. So this E out here stood for our sample space, and A, B, C, D, on, that's what the dot, 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 or ellipsis means, are all the events that occur in that sample space. So what we want to do now is we want to describe using set notation the sample space of each of the following experiments. So for part A, we have the number observed when a die is rolled. So if we're going to set up the sample space of that, we have our sample space is the set of 1, 2, 3, 4, 5, or 6, which is all the numbers on a 6-sided dice. For B, we have our sample space is the result when 2 fair coins are tossed. So you could find this using a tree diagram, where you could have heads followed by a head, you could have heads followed by a tail followed by heads, or a tail followed by a tail. So there's 4 outcomes there. For part C, we have the sample space being the number of girls in a class of 20 students. So there you could technically get 0 females in the class. You get 1, 2, 3, and to save time I'm going to use 3 dots to say that it continues on that pattern until you get 19 or 20 out of 20 students being female. For part D, we want the sample space of the number of emails received in a 24-hour period. So the sample space is going to include, it's possible to get 0 emails, 1 email, 2 emails, 3 emails, etc., etc., and you could continue that pattern on forever. That's also what we're going to call a discrete distribution. And that's because it takes on discrete values. It's not possible to have 0.5 or 0.8 of a phone call. So you can either have 1 or none. You could get 2, 3, 4, 5, and 6, but you couldn't get 6.8 of an email. And lastly, we want the sample space of the time taken in hours to complete your homework. So our sample space here is a little bit different, and we'll explore this more, but we can set this up so that t is the time, and we can say that such that t is greater than or equal to 0, and that is a way of representing the fact that your time to complete homework could be 0, it could be 1 hour, it could be 1.2 hours, it could be 1.234 hours, it could be 6.87 hours. You just don't know what it is. So that's a notation to say that the time taken could be anything that is greater than or equal to 0. For that, we can call it a continuous distribution. It can take on any value. So if you have the right equipment, you could time that right down to being 0.7892 hours. So that can take on any value, unlike our emails, which could only take on a discrete set of values. Next, we want to look at different events that could occur in these experiments. So we have the same sample spaces, but now we want to look at events. So for the first one, we want to create an event that could occur when you observe a number when a die is rolled. So we could call our event A being getting an even number. And that would be the set of 2, 4, and 6 for a 6-sided dice. For B, we want an event that occurs when you toss 2 coins. And we could say the event A is getting at least 1 tail. If we do that, we could consider getting a head followed by a tail followed by a head, or 2 tails also satisfy getting at least 1 tail. For part C, we want an event that has to do with the number of girls in a class of 20 students. And we could say that our event A is going to be having 5 or more girls in the class. So for that, we can see that the minimum is going to be 5, and then you could have 6 and 7 and so on until you got 19 or even 20 out of 20 being girls. They would all satisfy the event of 5 or more girls. For part D, we want the number of emails received in 24 hours, and we want an event for that. So our event A could be getting less than 30 emails. So here we need to be careful. It doesn't say less than or equal to 30 emails. So we could get 0 emails, 1, 2, 3, on and on and on, up to 29. So there's a little trick there that if you got 30 emails, that doesn't satisfy getting less than 30. And finally for E, the time taken in hours to complete your homework, we want an event for that. So our event, which we could call A or any other letter in fact, we're going to say that it takes less than 2 hours. So for that, we're going to use that special notation that you probably haven't seen a lot of, that T such that 0 is less than or equal to T is less than 2, because we know we can't have negative time. Alan and Bob also introduced us to the concept of probability. So the probability of an event is simply a measure of the chance that that event will occur. So for an event A, the probability can be represented mathematically using this fraction. So this says that the probability of A occurring is equal to the number of outcomes satisfying A over the total number of possible outcomes in the sample space. So there are two important rules when we come to working with probability. The first rule says that all probabilities are between 0 and 1 inclusive. So that means the probability of any event A sits between 0 and 1, and both of them are included. The second rule says that the sum of all the probabilities always adds up to 1. So if I take all the probabilities of all the events in our sample space, the probability of A plus the probability of B plus the probability of C, on and on and on until I've got all of them, if I add them all up, they will always total 1. So when we're trying to determine the probability, it's best done by inspecting or considering the sample space. So we'll just take a minute to pause and interpret what probabilities are. What does a probability of 0 or a probability of 1 actually mean? If the probability of event A is equal to 0, then there is absolutely no chance that event A will occur. Likewise, if your probability for event A is equal to 1, then it is guaranteed or it will definitely take place. When we work with probabilities, they're more likely to be somewhere between 0 and 1. So, if probability of A is close to 0, then there is only a small chance that event A will occur. If the probability of an event A is equal to 0.5, then event A is just as likely to occur as it is not to occur. Alright, so that's really embodied when you flip a coin. You've got a 50% chance of getting ahead and a 50% chance of not getting ahead, which would be getting a tail. Finally, if your probability for the event A is close to 1, then there is a large chance that A will occur. So now we want to have a look at some probabilities. So if we consider the experiment of rolling a fair six-sided die, the sample space is equal to 1, 2, 3, 4, 5, and 6. We want to then determine the probability of rolling a 4. So the probability of rolling a 4 is going to equal the number of outcomes satisfying that, which is only 1 in the sample space, out of a total of 6. The probability of that event occurring is 1/6. For part B, if we determine the probability for rolling a 5 or more is going to be equal to 1 and 2 events satisfy that out of a total of 6, which is going to equal 1/3. Finally, if we determine the probability of rolling a prime number is going to be equal to, and now we need to consider just exactly what are prime numbers. A prime number is any number that has only itself and 1 as factors. The thing to note here is 1 is not actually considered prime. So for this, when we do our set of prime numbers, we only have 2, 3, and 5 as being prime numbers. So therefore there are 3 outcomes out of a total of 6, which gives the probability of getting a prime number as being a half. So the interpretation of that is it's just as likely that you get a prime number as you don't when you roll a dice. So that's the end of this video, and now you should be able to do the following. So you should be able to identify a sample space, and that is listing all the possible outcomes for simple experiments. You should also be able to use set notation to list events within a sample space. You should also be able to determine the probability of an event based off the number of desired outcomes. And finally, you should understand the rules governing probabilities and their distributions.